Section 11.8, Power Series. Now, the remainder of this chapter deals with power series of one form or another. They come in special names: Maclaurin series, Taylor series, power series. All Maclaurins and Taylor series are types of power series. So we start off, a power series is always centered at a location. In this case, we centered at A. Okay, centered around A, power series at A. They all mean the same thing. So we look at this summation, n equals 0 to infinity, c sub n, x minus a to the power n. And you can see that that notation, that compressed form, the x minus a tells us where we're centered at. C sub n is some constant on each of the terms. If we expand this out, this becomes c naught plus c1 x minus a plus c2 x minus a squared plus c3 x minus a cubed. And the c naught, c1, c2, c3, they could be the same number, they could be different numbers, they are just constants. So we look at our first series here and say, okay, here's a power series. Where is it centered? Well, the key is this part right here. In other words, what would you plug in for x to make that 0? And we can quickly see that, hey, it's centered at x equals 5. We could play the game and clean it up. And you get 2 to the n, x minus 5 to the n. And then it's a little easier to see that this power series is centered at 5. Knowing where a power series is centered is very important on some of the computations later on. Our next one here says, well, is this a power series? The summation of x to the n. If we expand it out, that's 1x, x squared, x cubed, x to the fourth. The answer is yes, that is a power series. We know it's centered at x equals 0, or sometimes you'll say a equals 0. But we also know something else about that series. If you look at it, this series is a geometric series. So it's really a geometric power series. Now, when we deal with power series, they always have a variable in it. Okay, so in other words, there's an x. Now, being a geometric power series, you can tell me some things about it. So in other words, we know that a is equal to 1, and we know our r value is x. We know it'll converge if the absolute value of x is less than 1. And we know that the sum of this thing, based on formula, is a over 1 minus r. Or in other words, we get our sum is equal to 1 over 1 minus x. So we have this geometric power series, x to the n, starts off at 0, that's important, is equal to 1 over 1 minus x if the absolute value of x is less than 1. So we now know something about that power series, that geometric power series. Now, at the beginning of this chapter 11, I told you that there are certain series that we can find the sums for. Geometric series, telescoping series, and now we're to power series. Now, in this case, this all boils down to a geometric. So if I looked at it and said, hey, what is the sum of 1/2 to the n? Starts off at n equals 0. We have this formula. We know it's 1 over 1 minus 1/2. In other words, what do I plug in for x here? Plugs in for this other side of the equation as long as the absolute value of x is less than 1. And so I can find the sum of that power series if I want. So this ends up being 1 over 1/2, which ends up being a sum of 2. Now, for every power series out there, we only have 3 possibilities for convergence. The first condition is the series will only converge where it's centered. Now, every power series will always converge where they're centered. If x is equal to a, you plug that in, then you're going to get 0 for all the terms of x minus a to the n. So if we flip back to the previous page, all of these terms that have an x minus a on them, if x is a, all of those terms are 0. And you're left with just whatever c naught is. So if you always plug in your x value where you're centered, that power series will always converge. We can also have this power series converge for all x values. In other words, it would not matter which x value you plugged in. Okay, so that gives us our idea. Now, with both of these cases, every power series has an interval of convergence. So this interval here for part 1 is just a single item, and it's just the set that contains just the letter A. In part 2, this interval is the interval from minus infinity to infinity. In other words, it is the entire number line. So for part 1, when it converges only where it's centered, the interval is just the single item. For part 2, when it converges for all x values, then we have the interval from minus infinity to infinity. That is our interval of convergence. And in the last case, which is the more interesting case, is there exists some positive number r such that the series will converge if the absolute value of x minus a is less than r, and diverge if that absolute value of x minus a is greater than r. Now, first of all, we look at this and say, well, absolute value of x minus a less than r. You do need to know how to get this without the absolute values. I see students make a lot of errors on this every time. So this basically says, if I want to get rid of the absolute values, I go minus r less than x minus a less than r. At this point, I can add an a to everything. So a minus r is less than x is less than a plus r. And so this interval of convergence right here, the basic interval of convergence I should say, is from a minus r all the way to a plus r. Now, if you think about this on a number line, here's what we have. Every power series is centered at a. This radius convergence says I'm going to go out a certain distance, both sides, both directions, a distance of r. So this right here is a plus r, this value here is a minus r. And we know if you're in between those two spots, if I pick an x value between a minus r and a plus r, then I know that this power series converges. And we're guaranteed to converge. So just by knowing the radius of convergence, that's r, and the value of a where it's centered at, we've got some information. I know every x value in that green section will converge. I also know at this point that anything beyond that green section, in other words, on both sides, will diverge. So on the intervals from a plus r to infinity, and the interval from minus infinity to a plus r. Now, that's where this thing will diverge. It's guaranteed. it's going to diverge. And if you notice, we've talked about this entire number line except for two values. We haven't mentioned anything about a minus r and a plus r. And what I now know is that the convergence or divergence at x equals a plus r and x equals a minus r needs to be tested. So at the two endpoints of the interval, we don't know if it will converge or if it will diverge. We have to do more math to figure that out. Now, I mentioned that this value of r was called the radius convergence. So this positive number r is our radius convergence. So radius is equal to r. In case 1 and case 2, we also have a radius convergence. In case 1, the radius convergence is 0 because you're sitting at where you're centered, you're not going out any direction on either side. In case 2, the radius convergence is infinity. So what we have now is a power series. Every power series will have a radius convergence. 0 means that it only converges, that series will only converge where it's centered. Infinity means it'll converge for any x value. And if it's some number r, now remember it's a radius, so it's got to be positive. If it's some number r, then there is an interval from where you're centered, a distance of r both directions, that you're guaranteed to converge if you're inside that interval. If you're outside that interval, you're guaranteed to diverge. But if you're the endpoints of that interval, you have no information. You have to do some more work. Suppose that we're given a series, summation c sub n, x minus 3 to the n, from n equals 0 to infinity, and we're told that this series converges at x equals 5. Now, just by writing our series in here, we know that it's centered at a equals 3, or in other words, x equals 3. And suppose we're told that it diverges for x equals 7. So we're given a point, an x value, where this series will converge, and we're given an x value where it will diverge. Now what we want to do is to talk about the rest of the number line. For what values of x will this series converge or diverge? In other words, what do we know for a fact? So if I look at a number line here, I put my 3 on it. That is where we're centered. And I know that here is x equals 5. Now we're told in this problem that converges. So that means that this length right here, which is 5 minus 3 equals 2, well, the way these power series work, if you know one spot converges, that spot all the way to where it's centered will also have to converge. So right now I know the radius convergence is at least 2. It can't be any smaller. You cannot have a power series that converges for some numbers, skips some numbers, and then converges elsewhere. This interval of convergence has to be connected. So since this distance is 2, I can come off this other direction, a distance of 2, which gives me a 1 here. Now at this point, I don't know anything about x equals 1 because that is a possible endpoint of that length. And so right now I know the values of x that converge are, well, 1 less than x less than or equal to 5. Now, the equal we get because the problem told us it converged at 5. If we write this in interval notation, it is parentheses 1 comma 5 with a bracket. So that information about convergent x equals 5 tells me everything that's boxed in blue. Now, this problem tells me it also diverges at 7. So if I come over here and put a 7 here, I know this one diverges. Now, if you look the distance from 7 to 3, so if I take 7 minus 3, that's equal to 4. So if I come off a distance of 4 this way also, so 3 minus 4 is minus 1. And so right now, just that information says that I now know the radius convergence which we figured out that it had to be at least 2. I know it has to be less than or equal to 4. It can't be bigger than 4, because if it's bigger than 4, then 7 would have to converge. Because when you converge with the radius convergence, it's from the center out to the ends of that radius convergence. So this information that I have right here, x equals 7 diverges, x equals 5 converges, gets me to here. Now, if I didn't know anything about converging, then all I could say is the radius of convergence had to be less than 4. But this tells me some information. It tells me some important information. I now know that the x values that diverge are x. From our problem, we know it's diverging at 7, so x greater than or equal to 7, and x less than -1. Once again, -1 we don't know anything about because we got that number just based off of our possible radius of convergence. The problem told me that 5 converged, the problem told me that 7 converged. So 7 diverged. So 7 diverging gives me that information. Now you're noticing is that there's some part of the number line that we don't know. If I look back at this list, this section right here, between 5 and 7, and between 1 and -1, and including 1 and including -1, we don't know. We don't have enough information to say anything about that converging or diverging. So for 5 less than x less than 7 and -1 less than or equal to x less than or equal to 1, we do not have enough information to decide convergence or divergence.